Morning, everybody. My name is Ben Wallen, and I am your speaker today to deep dive into the world of flex rigid PCB design and manufacture. So just a little introduction about myself. So I've been in the industry now for a good 12 years, manufacturing very high complex PCBs for the industry. My current role at my employer Graphic is an applications engineer. So an application engineer is working with designers to make sure that your designs are industry compliant, make sure that they are repeatable and manufacturable on the shop floor, and just to ensure that the data files that you are producing can flow through the engineering tooling system without any friction. We want very much in the case here at Graphic that we want to push what we call clean data sets. So working with designers to make sure that the design rules that you're putting into your designs are correct so that we can then have good yields when we come around to manufacturing designs. Right, so first of all, I'm just going to quickly just give you a little bit of information about Graphic and tell you a little bit about ourselves. So Graphic is based in the UK. We are in the bottom left-hand corner, as you can see on the map there. And we were one of the original PCB manufacturers here in the UK, established in 1968. We have a very, very rich heritage when it comes to PCBs. Our founder, Rex Rosario, used to work alongside Dr. Paul Eisler, who was accredited with the invention of the first circuit board. So we have a very rich heritage from Rex working with Dr. Paul Eisler to then starting up Graphic in 1968. So in just over 2 years' time, we would have been in business for 60 years, which is a remarkable feat these days in Europe when you're seeing PCB manufacturers go out of business left, right, and centre. So it's very, very good that we are here to support the UK, Europe, and beyond as well. So Graphic is seen as one of the largest UK PCB manufacturers on one individual site. At our site in Crediton in Devon, we have a purpose-built HDI facility for manufacturing very complex, high-density, high-complexity boards, mainly for the military and aerospace defence. We have all the international approvals here, and we are regarded as one of the technically competent manufacturers of critical mission PCBs. Okay, so here at Graphic, and what I do for myself as an applications engineer is we offer extensive DFM support. So we are working with designers right from the point where a design is a concept and hasn't actually been physically laid out, where we are working right from the start with the materials to then working out the design parameters. And that's what we offer for amongst all of our application engineers that we have here at Graphic. We do have some very competitive quick turn lead times. So we can offer standard lead times as well as quick turn lead times that come as a premium. It just means that your orders can go around the manufacturing site a lot quicker than a standard order. So over the last 2 years, Graphic has invested 5.5 million into equipment here at Graphic. This is things such as the very first horizontal electroless plating line being installed at our facility over the last 12 months. It's the first horizontal electroless plating line in the UK, and it's now up and running, and we are using it on a daily basis. So we are predominantly a high mixture of products at low volumes. As I said earlier on, prototyping can be done on quick turns, and we typically run up to around about 70 panels is our forte. Every single account that we have here, every single customer will have their own commercial team that will support them with the day-to-day runnings of the accounts as well. So we are very interested to see if we can help you with any of your high reliability applications. With the extensive investments that have gone into the plant over the last couple of years, we have built extra capacity. So we are looking to fill up our factory with more complex designs that you may have for us in the future. We are definitely not the cheapest when it comes to the lower technologies. Graphic bases its core product types on very complex designs, multiple laminations, lots of processes. That's where we start to be competitive with pricing and for on-time delivery. So our excellence comes into our quality and on-time delivery. So for 2025, we've had over a 96% on-time delivery. If you have any designs, any prototypes that you might want us to have a look at, please reach out to us to our sales at graphicplc.uk. And if you reference Fed into the subject title, we will prioritize your inquiries. just to let you know a little bit more about the wider group. So Graphic is part of 6 PCB manufacturers around the world, which is a really good scenario for us for technology sharing, for equipment buying, and also working together for certain customers that might want to dual source. So just to go over those individual plants then, so we've got Graphic, as I mentioned, here in the UK. We teamed up with Symarchus, again, another very prestigious European PCB manufacturer, back in 2007. So Symarchus based in Castelvedro in Italy. We teamed up together to build DSG, which stands for Don Juan Symarchus Graphic, which is a purpose-built HDI facility out in China, which is a very famous PCB manufacturer for pushing technologies and producing some very, very complex PCBs. We've also got our site in the US, which is Symarchus Inc., based in San Diego. And in the last couple of years, we've added 2 new PCB manufacturers to our portfolio. Again, another very prestigious PCB manufacturer in Diconnect in Switzerland, who focus mainly on flexible PCBs and miniaturization as well. So predominantly for the medical market, building implants and defibs, things like that. And then it was only 6 months later that we then acquired Air Medtech in South Korea. So we've got a very good group of high-end PCB manufacturers, and the goal of our group is to become one of the biggest in the world over the next 5 to 10 years. So watch out for all of these PCB manufacturers and where we might be going. Okay, so to dive into today's subject, which is flex rigid manufacturing. So Graphic was one of the very first PCB manufacturers to get the accreditation to producing flex rigids. Graphic has been producing flex rigids now for, I'd say, 25 to 30 years, and is approximately around about 35% of the products that we produce on a day-to-day basis. Okay, so the particular topics that I'll be covering today in relation to flex rigids is materials, bend limits, processing. So there'll be various slides showing you pictures of the various equipment and processes that we will be using to produce flex rigids. What's important is the design of these flex rigids and also the manufacturing drawings as well. So how you are requesting certain features or certain design features to be produced all has to go down on the manufacturing drawings and be crystal clear exactly what you're asking. Then I'll cover compatible technologies with flex rigids. So these are other technologies out there that are available that can be included on flex rigids. And then we're going to go through some stack up examples and some flex rigid examples as well later on. Okay, so starting with materials then. So I always say that when you are creating a brand new design, a new flex rigid design, the very first thing that needs to be established is your construction, to make sure that we got all the dielectrics correct, make sure that the impedance has been forecasted and is suitable for your design. And getting that material base is the very first step to then creating a PCB. So to go through the materials then, one of the key materials in a flex rigid is the flexible materials, the material that bends effectively. So flexible laminates, we produce them here, we don't produce them, we use adhesiveless polyamide films to the IPC standard, which is IPC 4204/11. Now there are other flexible laminates out there. You can have adhesive laminates, so flexible laminates with adhesive already on them, but the 4204 is the slash codes for flexible laminates. They are available in a variety of different sizes. They are made of polyamide films. They can typically be 25 microns or thinner. The more common ones that are being used these days are the 50, the 75 micron, and the 100 micron. However, there are thicker available laminates out there as well. What you have to remember with material lead times, and flexible laminates can have a relatively long lead time. The thicker laminates will have a longer lead time. When you are requesting flexible laminates with split copper cladding, so i.e. you would have a 80 microns copper one side of that flexible laminate, 35 microns on the opposite side. Those are typically made to order, so we'll have a longer lead time again. So the key thing really is to try and keep the copper weights the same. And if you don't need to go to thicker flexible laminates, then don't, because then you're just going to add extra time with getting those materials shipped to your PCB manufacturer. Okay, so then you've got the rigid laminate, so flex ridges. We've got the flex in the center. Sometimes it can be offset, but then the rest of it is all built with typical rigid laminates. So most rigid laminates are compatible for flex rigid applications. Typically, what you will see is high TG-FR4s or polyamide glass reinforced rigid materials. However, we are seeing a big trend at the moment where lots of these flex rigid designs are becoming high-speed applications. So we are seeing lots of designs now that are flex ridges that have RF networks and require higher speed, low loss materials in the rigid sections. The prepreg, so the prepreg is the bonding agent. So that's between your copper cladded laminates that have been imaged and etched. The prepreg in particular for flex rigids, and I'm talking in and around the flexible sections, typically need to be no flow or low flow prepregs, i.e. they have a restricted flow rate. Because when you're coming around to PCB manufacturing for flex rigids, there's lots of depth milling involved. And the last thing you want to have is resin flowing onto the flexible section that might then affect its bending effectively. So what you will have is low flow prepreg in and around the flexes, and these are apertured as well to allow for techniques for depth milling. And then the last key thing for flex rigids is cover lays and bond plies, and you do also have cast adhesives as well. So cover lays and bond plies are, again, exactly the same as the flexible laminates. They're comprised out of Kapton films, and they will either have a single or double-sided adhesive layers. These adhesive layers are typically acrylic or epoxy, and you've got the IPC slash codes for those cover lays there. Some of these adhesives will have flammability ratings as well, and some of them will not. So that's why some cover lays will have a VTM rating, which stands for very thin material ratings. But as you can see, there's a big mixture of materials being used in flex ridges. Flexible laminates, rigids, prepregs, cover lays and bond plies. And when you mix all of these materials together, yes, they might all individually have flammability ratings, but when you put them all together in one construction, it's not possible to add the full UL marking. It is possible to get UL markings for flex rigids. It's quite an extensive process. It's expensive. It takes quite a long time. You have to build samples of that particular construction and send it away for testing. And then at the end of it, you will get an individual UL marking for that flex rigid construction. However, should that design ever change, copper thicknesses, a dielectric change, that particular UL marking is no longer valid for that construction. So that's why you typically don't see UL markings on flex rigid products. Okay, so moving across now to the copper foils, and in particular, what we're going to be talking today is the copper foils on flex rigids. So flexible laminates, at Graphic, we always like to work with rolled and annealed copper. There are flexible laminates out there that have electrodeposited copper, but as you can see from the pictures on the right-hand side, the rolled and annealed copper has a in-grain plane direction. So a direction of the copper grain, effectively, which makes it brilliant for flex ridges in particular. And then on the rigid laminates, you'll just have your typical high temperature elongation copper. If you're using your higher speed, low loss materials, then you're going to have a lower profile on those copper cladding, which is much better for running faster speeds. Okay, so just to show you then how the rolled and annealed copper is produced. So this is produced by copper manufacturers, and as you can see, they are produced on rolls, and then the RA copper is applied to the polyamide films. So as I mentioned before, the rolled and annealed copper has a grain structure and a smooth surface, which is ideal for dynamic and flexible circuitry applications. So with that grain direction, you get extra flux ductility. It supports more tighter and repetitive bends. And I will cover this a little bit more of the benefits of the copper grain direction. Okay, so as you can see here, so this is an example of a couple of flexible laminates. They have been through inner layer processing. So we've had the photodefinable films applied to the surface of the rolled and annealed copper. and then through LDI's develop etch stripping, we then have a fully defined inner layer copper pattern. So as you can see, there's some examples of inner layer flexible laminates. So just some pictures of the photomet room. So the clean rooms, that's where the laser direct imaging happens. So as I said, we have photodefinable films where your copper patterns are shone down onto these photodefinable films to then effectively define what is going to be copper and what is going to be etched away. So you can see the clean room in the background of the right-hand picture. That's where the layers will come out. They'll go through the developer, then through the cupric etch chamber, as you can see in the middle. And then we have to come around to stripping away the photodefinable film that we don't want to leave on that particular layer. Okay, so moving into bend limits. So there are some key IPC specifications that you need to be aware of. From a designer's point of view, you have the IPC 2223, which is the design standard for flexible and rigid flex printed circuit boards. But then the manufacturing specification that you should always be referencing on your drawing for flex and flex rigids is IPC 6013. So the next slide is going to be extracts from IPC 2223 for calculating minimum bend radiuses on the flex. So as you can see in the picture, you can see the flexible sections clearly bending. Effectively, there are guidances and calculations for working out what your minimum bend can be on your flex rigid. Okay, so to work out the minimum bend of a flexible section, you have to take the total flexible thickness. So that's the flexible laminate thickness, the copper thickness of the rolled and annealed copper, and then the coverlay thickness. So the coverlay will then be over the top as a protecting insulating layer over the exposed flexes. So in order to work out what your minimum bend radius would be on your flex rigid design, when you have a single-sided flexible layer or a double-sided flexible layer only, you take that total thickness and then you times it by 10 to give your minimum bend radius. So in this example, the assembly of the flexible section is 170 microns. You times that by 10 to get a minimum bend radius of 170 microns or 1.7 millimeters. It's not uncommon for designs to have more than 2 flexible layers. I'll show you some examples later on where there's a lot more than 2. But when you have more than 2 flexible layers, i.e. more than 2 flexible laminates within a flex rigid construction, then the total thickness has to be calculated slightly differently. So when you have over 2 flexible layers, you have to then take the total flex thickness, the same as before, and then you times it by 20 to give the total, the minimum bend radius. So the flex assembly in this instance is 315 microns. So you take the times 20 multiplier to give a minimum bend radius on this particular construction at 6.3 millimeters. There is potential sometimes to push the minimum bend radius. I've seen designers get away with it in some instances, and I've seen designers not get away with it. So it's very, very important to make sure that you are following the guidance of IPC, because the last thing you want to do is to have a flex rigid that then starts to break when you start to bend it. So very, very important to follow the minimum bend rules. Okay, so what happens if you push the bend limits? So if you push the bend limits on a flexible section, what we have seen before in those instances where the designers have not got away with it is you might tend to see copper cracking. So you might see the copper cracking on the flexible laminates, and then that might ultimately produce high resistance shorts. So very, very important to make sure you're following the guidance from IPC 2223, and always do check with your PCB manufacturer on your bend radiuses that you are using in your design. Okay, so there are 2 key types of flex rigids when it comes to the assembly. The main and most common is a flex to install. So this is where you are bending the flexible section into position, and that is the only time that that particular flex rigid is going to be bending. You then also have what's called dynamic flexes. So dynamic flexes are moving, they are bending, they could be oscillating many times over the life of that particular PCB. And it is very important to let your PCB manufacturer know if your design is a flex to install or if it is a dynamic flex. And the reason why it is important to let your fabricator know this, because the minimum bend radius calculations are a lot different for dynamic flex as opposed to flex to install. What is also something to take into consideration is your flex rigid might just be bending once when it's being fitted into its application. However, I believe, and we believe here at Graphic, that when you have those flex rigids that are flex to install, but are placed into high vibration environments, then perhaps you should be considering that particular application to be a dynamic flex, given the levels of vibration that that particular PCB might undergo. We have done lots of research and case studies here for particular flex rigid applications. And there is a particular application where we have a flex rigid that is working under very extreme environments. So subjected to G-force, it goes on to a jet fighter. So this particular flex rigid was being originally built with acrylic-based adhesive, and we were getting failures on this particular flex rigid. And it wasn't to do with the high frequency vibrations that it was suffering, it was the low frequency vibrations. So what we looked to do then for this particular design was to use an epoxy-based adhesive in the theory that those low frequency vibrations would be absorbed more by the softer adhesive. And lo and behold, it worked well. And now we are producing these particular flex rigids with the epoxy-based cover lane. Okay, so after those inner layers are imaged and etched in our photo mech room, we then have to go through AOI. AOI stands for Automated Optical Inspection. So this is where we are scanning the etched and imaged layers against the Gerber files that you have provided to us. At this point, we are looking to make sure that any over-etching or under-etching hasn't been processed, and we are making sure that the conductor widths are meeting IPC and your particular requirements. Okay, so there are different types of bonding methods when it comes to a rigid board, so a purely rigid board versus a flex rigid board. So going back to the materials that I mentioned earlier on, we use no-flow prepreg typically in flex rigids. There are a few flex rigid applications and designs where we are now using flowing prepreg in against the flex, but these techniques are still being developed. So still traditionally using the no-flow prepreg. So because we have the no-flow prepreg, which is apertured, and when I say apertured, we remove the material, in particular where the flexible sections are. And because of that no-flow prepreg that requires different bonding parameters, we have to use something that's called 4-slot tooling. So this is where 4 slots are used to then lay up the layers and then also the prepregs as well. So we are still on a 4-slot tooling system for flex rigids the majority of the time. So as opposed to rigids, which are done as pinless and you have welding sites, you do tend to get a little bit more movement between the layers on a flex rigid, because what you have to remember is you have harder rigid materials and the softer flexible materials all moving at different rates to each other. So in PCB manufacture, it's down to the fabricator to make sure that we are lining the layers together, making sure the layers are registering together, because we then have to drill through your pad stack and make sure that we are producing the angular ring requirements that you require for your design. So the way that we do that is we have copper fiducials and targets on each one of the layers. And we have these copper targets in all 4 corners of our production panels. We then use X-ray tooling to identify and locate the position of those targets to then give us a X and Y value that could be positive or negative, showing how those layers might have shrunk or stretched during the bonding process. Now, we get some very good data and analysis from our systems here to show us physically what is going on inside the boards. So as I said before, there are 4 corners where we are measuring the targets of these layers, and you get these very good reports now showing you 3D pad stacks to ensure that you're meeting the angular ring. The top right picture also shows something that does happen in manufacture is you can get a slight twisting of the layers. But it's very much the case for a PCB manufacturer when you're coming around to doing a batch one, so a first spin of a new design, you're never entirely sure how those layers are going to move in conjunction with the copper percentage areas on those layers and potentially the materials that are being used as well. So over time, batch on batch, PCB fabricators will optimize their layer-to-layer registration based off the results that you see on the screen here. So it automatically in the background auto compensates any layers that might have shifted a little bit more than we expected. Okay, so after all the layers are bonded, and there's a particular example here on the right hand side of a very complex 17 layer flex rigid that has 5 flexible layers all bonded together, and we have a series of buried and surface blind and buried microvias. And the key thing that we wanted to show you here is the depth milling process. So when flex rigids are produced around the shop floor, up until the depth milling stage, the boards look completely rigid because you have all the rigid material built up over the top of the flex. It is then when we come down to the depth milling that we come down and we hit targets. We use something that's called packing pieces here, which is our target for Z-axis milling. And then we depth mill down into this packing piece, and then we lift the rigid away, which exposes the nice, shiny, flexible sections. And there is a picture of one of our small depth routing machines there. So these machines are very specialized when it comes to depth milling. They have an accuracy of plus or minus 13 microns. Now that accuracy of the machine is only as good as how flat a PCB is when we put the panels onto the machine. The flatter the PCB is, the more accurate we can be with the Z-axis depth milling process. So this is why we always say to designers, if you can flood fill your signal layers as much as possible, then that always ensures that you get nice surface topography. You don't have any height discrepancies across the panel, which then allows our depth milling accuracy to be even more accurate. Okay, so moving on to design features for flex rigids. So a key thing for flex rigids, which differs from rigid designs, and there's lots of, I see it a lot in the industry at the moment, where people apply the same parameters to a rigid board as they would to a flex rigid. Now, going back to what I mentioned earlier on about the required 4-slot tooling, which does allow for a little bit extra movement of those layers, because we end up having those harder materials moving a little bit differently to the softer materials, we generally, and most PCB fabricators will ask for a larger pad size on a flex rigid as opposed to a rigid. Now, imagine a rigid board using homogeneous materials throughout will all move at relatively the same rates. As a flex rigid, you'll get differing materials moving at different rates. So this is why fabricators will ask for larger pad sizes, larger annular rings on flex rigids as opposed to rigid boards. Okay, so then moving on to the next thing. So a key feature on a flex rigid is the point at where the rigid section ends and the flexible section exits the rigid. And we call this the flex to rigid interface. Now, because we have a series of depth milling operations, and also because you have pretty much what we call the edge of a rigid section PCB, the flex to rigid interface should not have any features drilling too close to that rigid interface where we are going to be depth milling and the flex enters. This is all covered in IPC 2223. It's also covered in IPC 6013 as well. So what we typically say here at Graphic is the ideal distance for any SMD pads to that flex rigid interface is around about 800 microns, 0.8 millimeters. When it comes to the drilling, we typically say that the drilling should be around about 1 millimeters from the edge of the drilled hole to that flex rigid interface. Because the cover lay, and I'll show you some examples in a minute, is tucked into the rigid section by around about 1 millimeters to 1.5 millimeters, this is another reason why we don't want to have holes too close to the rigid interface, because the last thing we want is to drill through adhesive that then might affect the in-hole plating and the hole quality. Okay, so there's a picture in the top right-hand side that what I was referring to just a minute ago as the flex to rigid interface. So that's where the flexible section exits the rigid. So this is seen as the weakest point on a flex rigid design. So there are various different techniques for making sure that those weak points are reinforced effectively. So there are various different materials out there. We use EcoBond, which is a fillet relief, which is a bead of epoxy, which is applied to both sides of the flex rigid interface, just to add extra stability. Now, here at Graphic, we are seeing a big increase of flex rigid applications working out in space, so in LEO and GEO satellites. So there are specialized EcoBonds out there that have very low outgassing properties effectively. So if you do have a particular flex rigid that's destined to be working up in space, it's always important to use low outgassing materials in those applications. Okay, so going back to what we were talking about earlier on with the copper foil. So the rolled and annealed copper, as I mentioned earlier on, has a grain direction. And that grain direction, as you saw from the rolled copper, is in one axis. So different flexible manufacturers will have that rolled grain direction in one axis only, but the axis might change depending on how they are rolling and how they are cutting up their flexible laminates themselves. So this is in particular, a particular manufacturer. They have their copper grain direction always in the 18 micron axis. So what is a really beneficial option for designers is if you've got multiple bends on your flex rigid and you might have one particular flex section or one particular flex hinge might be pushing those minimum bend radiuses. What can be a really good tactic for designers to make sure you don't get failures on those particular type turns is to have the copper grain direction run along that specific flexible limb. And all you need to do as a designer on your manufacturing drawing is, like the green box, just show which direction you want the copper grain direction to be in, and obviously point to the key critical flexible hinge. However, whilst that can be beneficial for designs, it sometimes is not the case that it is beneficial for panelization. So when we are producing PCBs, we use our production panel, and we are always looking to try and squeeze on as many PCBs as possible, because the more PCBs we can squeeze on a panel, the less panels we have to then manufacture, which then brings down the overall unit price. But this particular design and the designers, they require that copper grain direction to be along a specific flexible hinge, as shown on the left-hand side. So we had to orientate the PCBs in that fashion. And as you can see, we can only fit 5 up on the left-hand side. But if the customer didn't need that copper grain direction, then we could have produced the panels as per the right-hand picture. So we would have got an extra PCB per production panel. And if you think about it over production runs, that's reducing the total panel count quite considerably, which also brings down the price. So please also do bear in mind, if you are asking for the copper grain direction to be in a specific axis, it might affect your unit price and how many PCBs you can fit up per circuit. Okay, right, non-functional pads. So there are specific rules when it comes to non-functional pads on flex rigids and also rigids as well. So the rules that we kind of pass on to our designers here at Graphic is when it comes to non-functional pads on the rigid layers, so any layer that is not using the flexible laminates within your flex rigid construction, we would always ask that you remove the non-functional pads. They are not functional, and effectively they don't necessarily need to be there. So by removing the non-functional pads, you end up getting a much cleaner cut because there's less copper for the drill bits to go through, so you get less wear and tear, which then allows for nice smooth in-hole plating as well. So on the rigid layers, we say remove your non-functional pads. Now, the key thing, this is the reason why we put this up on this slide, is when it comes to the non-functional pads on your flexible layers. So on the flexible layers, on your rolled and annealed copper layers of the flexible laminates, we would ask that you reinstate and keep those non-functional pads in place. So as you can see on the pictures on the right-hand side, we've got an example of where the non-functional pad is kept in on the left and where we don't have a non-functional pad on the right-hand side. You can see two very clear differing results of having those pads there. By having the non-functional pads, you just add extra stability to that interconnect and to that whole wall as well. So on your flexible layers, keep that copper on there, keep those non-functional pads present, as it will help for the in-hole plating. Okay, right, routing. So routing on flexible layers and across those flexible hinges. What is always very, very important when it comes to flex rigid design is to not inadvertently create creases or weak points on the flex. So when we are talking about the copper tracking and the routing over that flexible section, what we don't want to be seeing is sharp turns of the tracking. You want to see nice, smooth transitions of the tracking, nice, smooth arcs, because if you have sharp turns where the board might be bending, you can then inadvertently, as I said, create a weak point or a stress point on the flex. When it comes to the power and ground layers, so you might have shielding layers on your flexies. It is said that for extra flexibility is to use cross-hatching. And whilst cross-hatching is not a problem at all, it can cause certain complications when it comes to impedance matching. But then you can also as well, what we see a lot of the time is for cross-hatching is you can inadvertently create slithers or same net spacing issues, which then need to be cleaned up before manufacture. But we always kind of say it's not a problem to flood fill your power layers. In reality, we see it more often than not that flexible ground and power layers are flood filled, and it's not a problem to use that. When it comes to impedance matching across a flex rigid, what you will typically find is that it's not always the case that there are differing results. But when you're running a 50 ohm single-ended or say a 100 ohm differential pair from the rigid section on the flexible layers, from the rigid section across the flex, perhaps into other rigid sections, because you have differing reference layers, you may end up having different track widths required in the flexible section as opposed to the rigid, because in the flexible section, you might just have the cover lay and air as your reference because you've obviously depth milled and removed all the rigid material out. So there may be a transition in the width of your impedance lines required when you're exiting the flex onto the flexible section. Now, again, you don't want to have sharp transitions in the trace whips, and you want to make sure that those trace whips are transitioning within the rigid to not create those crease and weak points. So I'll show you some examples of it now. So the picture in the top is what I was talking about earlier on, about not having sharp angles when it comes to routing across the flexible layers. And what you do want to see is the example shown below there. So nice, smooth arcs, effectively, with nice radii, no sharp turns. That is ideal routing for a flexible layer. Now, when I was talking earlier on about the transition of your impedance lines when they exit the rigid onto the flex, what you don't want to be seeing is the picture on the left where you have a sharp, jagged transition, and you want to have a nice gradual transition from the trace whips as shown on the right-hand side. And as I said before, when you're doing these transitions, make sure they are happening within the rigid and not on the flexible section. Okay, the do's and don'ts, the things that are preferred and the things that are preferred. So we see lots of designs these days where drilling is put onto the flexible section. Now, it could be used for a variety of different reasons. It could be used for shielding. You might have actual components. You might want to be getting some connections along the flexible section. But what it does is it means that flexible section, if you've got drilling going through it, it has to be a plated assembly before we then carry on the rest of the bonding for the rigid materials. So it can cause lots of complications. Extra plating on the flexible section will increase the copper thickness, which will increase the minimum bend. When you also have plated flexible layers, because the copper is thicker, you then have to have thicker adhesive layers in the cover lay to encapsulate around those thicker copper patterns. So again, increasing the flexible thickness, which will then increase your minimum bend radius. again, we see quite a lot of designs, and I'll show you an example straight after this, where we have drilling on the flexible section. We have a flexible tail where they are also then assembling a component onto the flexible tail. Now, because you have that flexing of the flexible laminates, if it's plated and then you've got SMD pads on that tail, you can then effectively get some issues when it comes to the surface finish. So a universal finish that you will see is electrolysis nickel immersion gold. And what you can see on surface finishes being applied to the flexible laminates is you can see nickel cracking as a concern. Going back to flexible tails again, so it's very, very common that you'll have a rigid section, a flexible section that will then come to a connector end. Now you have ZIF connectors, Molex connectors. We see all different types here effectively. And when you have those particular flexi tails on a flex rigid design, the best routing and profiling technique is to laser route those particular flexible tails. Laser routing as opposed to mechanical routing, you can be much more accurate. It's a much cleaner cut as well, so you don't get as many burrs and feathers that you would get with a mechanical router. And as we know with these Molex and ZIF connectors, the profiles and the linear tolerances around these areas have to be very, very accurate. So this is why laser profiling is used for flexi tails. And here's a very good example. So you can see the rigid section, and this is panelized as a 5-up. And as you can see, the flexible layer is turned on itself, and we have a component that's being assembled to the flexi tail at the top of the design. So this is going back to what I was saying just a second ago. So we have SMD pads on that flexible tail. So this design runs a risk of nickel cracking by the fact that it is plated and they have SMD pads on the flexible section itself. Okay then, so moving on to compatible technologies now with Flex Rigid. So what we are seeing as time goes on is HDI structures are being included into Flex Rigids as per the example that I showed earlier on. So tighter pitch components are now being assembled onto the rigid sections of Flex Rigids. So it's now very, very common to see series levels of microvires along with buried vires to then get the routing out of these tighter pitch components. What can always be a challenging factor for designers is taking in those annular ring rules for the mechanical drilling and having larger pad sizes that is required for flex rigids and being able to meet annular ring requirements of IPC is a very tricky scenario. So it's usually the case now that if you've got a component that uses a 0.8mm pitch BGA component or less, then you're going to have to start to use the blind and buried approach when it comes to your via spans. It's because just large annuluses are needed on mechanical drilling when it comes to the flex rigids. So we see lots of resin-filled through vias and buried vias on these HDI structures. And a key trick for flex rigids and for rigid boards as well is when you have those resin-filled through vias, because you have extra plating going onto those layers, it's always quite important to have a flowing pre-preg underneath those via termination layers. What that flowing pre-preg does, as it flows during the bonding process, it creates a nice flat surface topography of those plated layers when it comes around to etching. Now, because we have a mixture of materials in flex rigids, you can get some distortion of the patterns as the pad stack is built up. So ensuring you have flowing pre-preg in the right areas does make sure that we have nice surface topography, which then allows for improved etching accuracy. Now, the no-flow pre-preg and the flowing pre-preg, it might be the same high TGFR4 material. However, they will have differing bonding requirements. So you'll have a no-flow bond, and then you'll have a flowing pre-preg bond. So it might not be the case that you need to have the flowing pre-preg. If you do, then we do need to go through extra laminations, which does cost a lot more. Okay, so other types of materials and technologies that can be included in a flex rigid. So here at Graphic, we use lots of specialized capacitance materials. So these specialized capacitant materials are incredibly thin. we work down to 6 microns capacitance materials that will then have copper cladding applied to them. There is specialized processing techniques for these ultra thin laminates, but we are producing them in flex rigid designs as well. So should you need specialized capacitance materials in your flex rigid design, it is possible to use these particular specialized materials in those constructions. But please do always check with your fabricator that your particular design is compatible with those capacitance materials. Okay, copper coin technology. So copper coin technology, for those who don't know about it, has been around for a good 15 years now. Adoption of it in the military aerospace sectors, where graphic is predominantly residing, is very, very slow. New technology adoption is very, very slow in the industry. However, this is a technology that's been around for a very long time. And what we are starting to see now is flex rigids having copper coin technology in the rigid sections. So what the coin actually does, so we have a pre-made copper coin. It can be of a certain profile. They used to be circular, i.e. actual coins, but now we're starting to see all shapes and sizes. Last week we saw a triangular coin with a couple of turrets sticking out of it. We've seen copper coins recently that look like Lego bricks with little towers coming out that will go underneath certain components. And the reason why they are built in is because the copper coin provides a thermal pathway for components that might be prone to overheating. So copper coins can be included into flex rigids, but what is a very, very important requirement for copper coins is to have flowing prepreg resin in those prepreg windows to encapsulate and hold the coin in place, which is a very, very important process when it comes to building the coins into products in PCB manufacture. So the way how it works is we would ask you to say, this is where a copper coin needs to be fitted into the design. We would then pre-route where that coin would be placed. And during the bonding process, we would use the resin from the flowing prepregs to flow up the sides of the wall of the coin, and then to hold the coin in place when the resin is cured effectively. We then have plating operations afterwards. So you would then plate over the top of the coin, and you would then typically have stitching vias in close connection to the coin. So you'll have the coin connecting to the plated copper, connected to the via holes that will be closed, that will then connect to your inner layers. And here's some examples of copper coins. As I said, they are built underneath components for drawing heat away from that particular component and creating a thermal pathway. It's not just copper coins. We are seeing other types of materials now embedded into the PCBs. We are producing lots of ferrite coins for electromagnetic purposes. Okay, so other types of materials that can be used in flex rigids. So we work here at Graphic with resistive foils. The main resistive foils out there that are on the market is Amigaply resistive foils and Tyser resistive foils. It's usually the case that a fabricator is set up to work with either one of those resistive foils. Here at Graphic, we work with the Amigaply resistive foils. Now, these copper foils, these resistive foils that come with a nickel chromate, will either come in 25, 50, 100, 250 ohm square. And then what we can do is we can etch resistor patterns or heater patterns with those resistive foils. So taking a picture in the middle at the top, so you can see the blue Wilkinson splitter network, which is used on RF designs, and the red is the resistors that have been etched and imaged to then connect down to that particular splitter network. So sometimes it can be better for a design that you use resistive foils to create your embedded resistors or embedded heater elements or embedded switches, like in this instance, as opposed to actually assembling resistors onto your boards. Now, there is challenges when it comes to working with these resistive foils. We have to work out the square areas of the certain heater element or of the resistors, which can be a challenge, but we have various guidance documents in place to do that. And you can also work with Amiga Technologies, or I believe they're Quantic now, for working out your pattern sizes. Plated cavities. So we are seeing lots of flex ridges, predominantly mainly ridges these days, RF designs, that require plated cavities to be produced. These plated cavities can also be produced on flex rigid designs as well. So the picture on the right hand side is just showing some typical edge plated cavities, but these cavities can be inboard as well, and can also be used, say, for example, if you have heavy copper layers within your flex rigid board, you might want us to depth mill down to that particular heavy copper layer, where you might then want to assemble a component. But there are various different types of cavities that we see. Please also make sure you're talking to your fabricator about what is possible when it comes to plated cavities. Another technology type that can be used on flex rigids, and again also rigids, is back drilling. So back drilling is a very useful technique for creating all these weird and wonderful signals within your PCB without having to go to the need of creating a design that has to go through many laminations. So when I say laminations, that's bonding and then bonding again and then bonding again, which is very, very expensive, lots of laps around the shop floor. So back drilling can reduce the need for all that extra processing by effectively drilling vias through a subconstruction or through via, and then using a back drill tool to break the in-hole plating connections to a certain depth. So what we always say is that we want to effectively minimize your stubs. And here at Graphic, we can kind of work to a max stub length of around about 100 to 125 microns. What I wouldn't want to see on a design is back drilling potentially coming to your flexible section. So let's just say you have two flexible layers within the middle of your construction. It's a 6 layer. I wouldn't want to see designers say, we want you to back drill from the bottom side to break the connection up to the first flexible layer, and then to not cut the copper on the next layer. So the reason being is because flexible laminates are very thin, and being able to control that depth is very, very difficult in between a polyamide film. So back drilling can be used to create all these signals, and it is compatible for flex rigids. In this particular example, as you can see at the bottom from the micro section, you have the through via as a resin filled and plated structure. And what this particular customer wants is they want the back drill structure as well to also be resin filled. So you've got a dual diameter resin filled structure, all for signal integrity purposes. Okay, another particular type of technology that could be used and introduced on flex rigids, we call it microfluidic technology, but effectively what it is us building a air gap or a air channel within the PCB itself. Now, for this particular application, it was used for monitoring and for analyzing fluids being passed through that channel. There is a resistive foil being used as a heater in there, and it gives back a reading effectively on the fluids that's going through there. Now, this particular type of processing, it can be used for many, many different things. I've presented this before to designers, and they've looked at building these air channels within their PCBs, potentially for coolant, for cooling down the particular PCB. But it's also quite useful on very high-speed designs as well, because as we know, air has a very stable dielectric constant. So we are seeing lots of rigid RF designs now where we have air-filled structures, where you will have specific RF tracking going through those air substrates. Okay, right, now to show you some examples of flex rigids that we produce here on a day-to-day basis. So this particular design is a 10-layer flex rigid. You can see in the build, the polar build on the left-hand side, you have the rigid section on the right, and then the flexible section on the right-hand side, showing the flexible laminate and the two cover lays either side. So this particular design, it has a 0.5 pitch BGA. So very, very tight, dense routing. So the designer had no choice but to stack the microvias on top of each other. And then as you can see from the microsection at the bottom left, they are also stacking those microvias on top of the buried, resin-filled and copper-capped buried via. So whilst we were happy to take this design on, because we know this design is not working in a harsh environment, it's basically just used as a handheld measuring equipment, we were happy to accept the design as long as the designers were accepting the risks of what they have done in terms of stacking. Because what they have done in terms of their stacking, and this is why we brought this up today, is definitely a no-go in the industry. through Z-axis expansion. So when boards are heated up and cooled down over the course of their life, the boards are stretching out and shrinking in. So you have to see PCBs as living, breathing animals. And if you can imagine in that microsection picture, the expansion of the resin would be pushing up onto those stacked microvires, which can then create stresses and strains. But because it's not working in a harsh environment, we were happy to build this board, but we show it as an example of what not to do. What you should be always looking to do is to stagger your via spans away from each other so that they don't negatively influence each other potentially in the life of that PCB. Okay, so this is an example of an 18-layer flex rigid, and we have 12 flexible layers within the PCB. And these flexible layers have 2 ounce or 70 microns rolled anneal copper cladding on those flexible laminates. So this is was previously what we call a book bind design, because effectively the design itself does a complete 180 turn and basically looks like a book. So when this design was produced many years ago, there was a technology, and there still is a technology now called book bind technology. So basically what you have is varying different lengths of the flexible laminates, so that when you come around to bending, you don't get any sort of issues when it comes to cracking or pushing the bend limits. So it becomes a bit of an issue when you're working with book binds, is you don't really want to be working with kinks in the production panels. So Graphic now, along with I'm sure many other manufacturers, will say book bind technology is a challenge that we don't really want to do anymore. So what we did with this particular design is we turned it into a traditional flex rigid. So what we did is we bonded all of the flexible layers together. So you can see the green on the picture on the right hand side shows the bond ply. So the bond ply is a capped on film with adhesive either side that allows all of the flexible layers to be bonded together as a single mass. Now, it's seen as an advantage to do that because what you can also see on flex ridge is what we call loose leaf, where you have air gaps in between the flexible sections. So you have the flexible laminate cover lay, and then you'll have that repeated many times within the construction. Now, what we do tend to see is you can create pink points when you have air gaps in between them. So we do say in some scenarios, it's better to have all the flexible layers bonded together in a single mass, because you evenly distribute the stresses and strains across that flex section. Here at Graphic, we have produced up to 40-layer flex rigid designs in the past. So it can be done. We have seen over in some of our other sites, we've seen up to 56-layer flex rigids. So it can be very complex. Okay, so we also see a lot more of these days, and that is a dual height flex rigid. So you can have certain rigid sections within your flex rigid design to be at varying different heights. So as you can see in the example here, the left-hand side, let's just say typically that's a 1.6 millimeter thick rigid section. You have the flexible exiting out of that rigid, and then it's going into a thinner rigid section, which let's just say, for example, is 0.8 millimeters total thickness. So there's lots of methods, quite standard methods these days for creating these dual height, or perhaps you might have multiple heights across the flex rigid that is now able to be produced. So even on these thinner rigid sections, they won't be classed as the outer layers because they're not, they're inner layers. We can still apply the solder resist over those different height rigid sections for assembly. Now, assembling of dual height flex ridges is no easy task. There are lots of assemblers out there that do have the capabilities, but please do always check with them that they are happy to work with dual height flex ridges when it comes to the assembly. Okay, so we were saying earlier on about an increase in high-speed, low-loss materials being used in flexi rigids. So the good thing with ceramic hydrocarbons, which is what Graphic uses a lot of, we use the Isola ranges, we use the Elite, the Panasonic materials, which are all very good low-loss, high-speed materials. They do tend to have a restricted flow anyway. So we're talking about the pre-preg here. When we are working with FR4 materials, you do get a very good flow in the resin. But when you move up to these higher speed materials, you do then end up getting a bit of a restricted flow rate, which is ideal potentially for flex rigids. So in this particular design, we've used those low loss, high speed materials throughout the entire construction, except for obviously the flexible laminate, and then produced the flex rigid with those materials. So it's not always compatible, these materials, for all flex rigids. Please do always check with your fabricator that they are happy to work with those materials in that particular construction. But it does kind of show that things can progress when running higher speeds on flex rigids. Okay, just one more kind of thing I wanted to kind of mention. So another key difference between flex rigids and rigids is the preconditioning of the circuit boards before use. So here at Graphic, we have our recommendations on what you need to do. For the bake times, we always say that the bake times to drive out the moisture from the PCBs before the assembly process should be anywhere between around about 115 degrees to 125 degrees C. But what is important for flex rigids is the amount of time needed depending on the number of flexible layers that you've got in your construction. So we would typically say if you've got one flexible layer in your flex rigid, the bake time should be a minimum of 4 hours at 115 to 125 degrees C. However, should you be adding more flexible layers to your design, those bake times need to go up. So our recommendations would be for every extra layer added onto one, you add an extra 4 hours above those original baking times. So very, very important to make sure that you are handling those PCBs before assembly, just to make sure that there are no issues of the PCB within the life of its use. And thank you very much for your time.